Okay, so now we're going to move on to the new, sort of one of the last things we got to cover here. It's a little bit weird, but we're going to talk about, and I kind of blurted it out last time, but let's just do it again more carefully. Momentum and center of mass, which I'm going to abbreviate COM, all capitals. Sometimes I forget and write CM, but I really am going to stick with COM. Now, you remember the center of mass we worried about before when we're doing rotations, because we said if something isn't rotating, we can treat it like a point particle at its center of mass. But if we apply a force to something away from its center of mass, we might torque it, and it might rotate. That was, remember how much y'all loved rotation and torque. Okay? But it also has a deeper connection to center of mass. So we'll go through this with just sort of a sample, sort of a wordy problem. Let's see. So two masses, M1 at V1 and M2 and M2, which is still, meaning it's not moving, right? They are like this on an axis. Okay, so let's put them on an axis here. X-axis. Let's say M2 is at the origin. Not moving, just sitting there, perfectly fine. And let's put M1 here. And it's at V initial. Right? And it's at some distance away. It doesn't matter. We're not going to do this numerically. We're just going to think about what it means. Okay. Let's see. So we look at this, and we say, what do we know about this system? Where's the center of mass? One more thing. M1 equals M2. They have the same mass. Okay, so where's the center of mass? Somebody shout out in one word. See if you can distill it down to one word, the center of mass. What is it? Middle. Excellent. I was going to say center, and mine is better, but I'll accept middle. Okay, so there, right there. So that a symmetric system like that, you can do it just intuitively. It's in the middle. If you wanted to calculate it, you could. Remember, so at the center of mass, it's 1 over the total mass times the position of each one times its mass. So this is at the origin, and this is at m equals this distance, and this one's at 0. So it's this distance times m over 2m, so it's half of the distance. Right? So maybe you remember doing that calculation. But for now, just intuitive is good enough. Okay, so the center of mass, we're linked. I actually wrote middle here, so very good, whoever that was, is in the middle. Excellent work. Now, what we're trying to think about now is how is the center of mass going to move? All right, let's see. In time delta t, let's think about time delta t. What is going to happen to mass 1? In time delta t, mass 1 goes how far? Vi delta t, right? Goes Vi delta t. Vi delta t. The center of mass goes how far? Again, intuitively, how far does it go? What is it? Intuitively, how far does it move? The center of mass. I was like yelling over when you were talking, so I don't know if you said the important part. What number goes in the front? A half. The center of mass, and this is not intuitive, that's why we're thinking about it carefully. The center of mass goes half the speed of that one mass. Right? So think about why. I think the most intuitive way to think about it is what if the mass 1 went all the way and hit mass 2 or stuck to mass 2? Center of mass would be there. So in that amount of time, mass 1 had to go all the way to here. How far did the center mass go? Half. Right? So it has to go half as far. Where are we going with this? I forgot, because I made these notes really last minute. Okay, so that's what's happening. That's what we care about. The center of mass is what we're tracking. How fast is it going? It's going at a half of VI. So after a perfectly inelastic collision. So hopefully you remember what that means. What's the perfectly inelastic collision? The perfect part is a superlative. It has a technical meaning. It means it's the most energy you can lose. Inelastic means you lose energy. Perfectly inelastic means it's the most energy you can lose. And that happens when the two things stick together. Right, so remember, perfectly inelastic collision, they stick together. And the reason that's the ones we're doing is, remember, when they stick together, you only have one unknown at the end of the problem. Each mass doesn't have its own velocity you have to solve for. There's only one velocity, which means we only need one equation. So we solve it with the conservation of momentum. Okay, so after this, they stick together, and the COM it's on the masses. It's wherever they are. Right? I mean, the center mass is now one object. It's like a point particle. So let's see how fast it's going now. Oh, I forgot to get out the things again. The speed. V center of mass is the final speed we would solve for in this perfectly inelastic collision problem. Remember we solved that one? And what was it? It was 1 over the total mass, 1 over 2m. That was the total mass. So this is in your notes if you went back. Times this mass times its initial, plus the other mass, 1, 2 times its initial, which is 0, not moving. So what do you get? You get that the center mass continues to go at a half VI. Right? Cancels 1/2 VI. Okay? So the conclusion, the big deal, the reason I'm getting all excited about this, if you can't tell, is that the center of mass travels at 1/2 VI the whole time. It doesn't change its velocity. So in this problem, it's an isolated system. The center mass just keeps going. Okay? Even though there's internal forces and big pressures in the thing, atoms fly off and it moves around, doesn't matter. The center mass just cruises along. So here I'll do the problem. I forgot to bring the little carts. Here's an perfectly inelastic collision. My hand is this cart. Let's see, you're going this way. This cart's stationary, and this one comes in. Oh, and it slows down, right? So where's the center mass? I was going to use my hand to show it to you. Here it is. The center mass is where my hair is hanging down, right? So it's going like this, and then it's oh shit, okay. This is too close to dancing. I can't do this. Okay, so this one is moving at V, and the center mass moves at half V. See how my head is moving slower than these? And then this slows down to half V, and we keep going. Okay, that was very effective teaching right there. Okay.